Cool. So we're going to start off with waves. And so the question is, what is a wave? What is a wave? And a wave is just basically a transfer of energy. I'll just highlight this. Transfer of energy without the transfer of matter. And when we're talking about waves, there are two types of waves that we care about. One is called a mechanical wave, and the second type of wave is the electromagnetic wave. And the key difference between an electromagnetic wave and a mechanical wave is that a mechanical wave requires a medium to travel through. So some examples of mechanical waves are sound, water, and slinkies. So for all these waves, you need some sort of medium for the energy to travel through. So for our sound waves, we need air. For water waves, you need water, and for slinky, well, you need a slinky. Electromagnetic waves, on the other hand, are special because they don't need they don't need a medium. So electromagnetic waves are basically all of our light waves. And if you remember if you've done it before in not unit 1, in year 11, where we talked about the electromagnetic spectrum, and that's that's basically all of our light waves, going from radio waves all the way to gamma rays, and that comes back in this lecture and comes back in unit 4. Cool. When we're talking about waves, there are two things that we care about. One is called a wave pulse, and wave pulse is just a singular wave. So if you imagine this to be some water, wave pulse would just be a singular wave that travels through the water. When you combine multiple wave pulses and you create a continuous spectrum of wave pulses, you create something called a periodic wave. And this is probably what you've seen before. So you just have a bunch of waves, bunch of wave pulses coming together, and that's just creating one continuous wave. Cool. There's one thing I want to make clear. So let's imagine that this is a water wave. So this is, I'll do it in blue. Let's imagine that this is a water wave. The question is the water moving? I know it might seem like the water is moving, but what's actually happening is the water is not moving. Even though the wave is traveling in this direction, or traveling to the right, the water is not moving. What's moving is the energy. The water is just traveling up and down. So if we have some water here and the wave comes, what's going to happen is that the water at this section is going to be lifted up and it's going to drop back down after the wave passes. The water is not moving from left to right. It's the energy that's moving left to right. Why? Because a wave is a transfer of energy and not a transfer of matter. So the wave is traveling this way, traveling to the right, and the water molecules are traveling up and down. And when we see something like this is what we call a transverse wave. Transverse, spelled that wrong. Yeah, I don't think I spelled that correctly, but it's a transverse wave. A reason why we call it a transverse wave is because the wave is traveling to the right, and the water molecules are going up and down. So the wave is traveling to the right, and the water molecules are going like this, going up, down, up, down, up, down. And because the direction of the wave, which is going to the right, and the direction of the particles, which is going up and down, because they're at right angles to one another, we call this a transverse wave. So a transverse wave is basically when the wave and the particles are moving at right angles to one another. The second type of wave we have is something called a longitudinal wave. So a longitudinal wave is when you have a wave and the particles and the wave is traveling in the same direction. And the most common example of this is sound waves. So this is what a sound wave looks like. So you have these sort of dots bunched up close together, and these dots are like air particles. And so you have these areas of compression, so when the dots are really close together, and you have places of rarefaction where the molecules are spaced out. And the reason why we call this a longitudinal wave is, let's assume that this is a sound wave and it's traveling to the right. What happens in a sound wave is that the molecules of, like the air molecules, they are oscillating left and right. They're going like this. And because the air particles, they're oscillating in the same direction as the wave is traveling, uh, these two directions are parallel. So you have this direction, which is left, right, and you have this direction of the wave, which is going to the right. And because they're parallel, we consider this to be a longitudinal wave. Cool. And what you can do with waves is you can calculate the period of a wave and the frequency of a wave. So if you remember in your your term 2 stuff, where you did EMF graphs, it's kind of the same thing. So if you remember this, you had some sort of like sine wave. You had voltage in the x-axis, you had time in the y-axis. You had voltage in the y-axis, time in the x-axis, and you had some sort of voltage, like 5 volts up here, and then -5. And what you did from this is you could calculate the period and the frequency. So the period of a wave is basically how long does it take for the wave to complete one cycle. And in this case, since this is one complete cycle and it takes 0.5 seconds, the period of this wave is 0.5 seconds. Sorry, 0.5 seconds. The frequency is basically a measure of how many cycles can we complete in 1 second. So the frequency of this wave is going to be 1 divided by the period, which is 1 divided by 0.5, which gives us 2. And the units for frequency is given as hertz. Cool. Yeah, this is pretty much what you've done in your EMF graphs. Essentially, the exact same thing. Cool. There's a few terminology that you have to be aware of when it comes to waves. I'll go through the easiest ones first. So amplitude. Amplitude is basically how big the wave is. The more specific definition is the maximum displacement of the particle from its mean position. And mean position is basically when y is equal to 0. So if I draw a quick wave, the mean position is this sort of x-axis. That's the mean position. The amplitude then would be the maximum displacement from this x-axis to the top. So the amplitude is this. So if you remember back to EMF stuff, that's basically like your peak voltage. Wavelength is how far the wave travels in one period. So if this wave was, let's say, 2 meters long, the wavelength of this wave would just be 2 meters. Velocity is just basically how fast does the wave move. How fast does the wave move? And it's given in meters per second. And the thing about velocity is usually constant. So the velocity of sound waves is about 340 meters per second. You don't need to know that, but it's usually around that. And the thing is with the velocity or with the speed of waves, you can't really change that as much. And you end up with getting this formula. Velocity is equal to frequency times wavelength, which shows you the relationship between velocity, frequency, and wavelength. This second formula over here, so velocity is equal to wavelength divided by time, that comes from the formula that frequency is equal to 1 divided by time. So if you combine these two equations, frequency is equal to 1 divided by time, and you combine this equation with velocity is equal to frequency times wavelength, you combine the two, and then you get this. And to be honest, this is probably the only calculations that you're going to end up doing in Unit 4, especially when it comes to waves. There's this, and there's about 2 other formulas that you need to know. Yeah, so as I said, not many calculations for this subject, for this topic. Cool. Now that we know that, what we want to know is what happens when we have 2 waves interacting with one another. And when this happens, we call this a superposition. So in this case, we have 2 waves. We have this red wave and we have this blue wave. Yeah, they're traveling together. They're traveling towards each other. And the question we want to ask is, what is going to happen when these 2 waves collide with one another? And what happens is these 2 waves are going to combine and their amplitudes are going to add. So let's just say that this red wave has an amplitude of 5 and this blue wave has an amplitude of 3. So what's going to happen when these 2 waves come together and they meet in the middle? It's going to result in a much bigger wave that has an amplitude of 8. Yes, essentially these 2 amplitudes just get added to one another. So if instead, I'll rub that out. So if instead this wave, this blue wave, was underneath, so if our scenario looked something like this, let's forget about the top part for a second. If the blue wave was under the x-axis, then what happens? So when they combine in the middle, what we're going to see is these 2 waves are going to add, and it's going to result in a smaller wave. And the resultant wave, when these 2 waves combine, you're going to get something that looks like this. So essentially what's happened is we have an amplitude of 5 over here, we have an amplitude of 3 over here. So you can sort of think of this 3 as -3. And when you add 5 and -3, you're going to get a final amplitude of 2. And yeah, so that's basically what happens when you have 2 waves interacting with each other. So what happens after? So we know that these 2 waves, they're going to come, they're going to meet in the middle, they're going to combine. Depending on if it's positive or negative, it will depend if the wave is getting bigger or the wave will get smaller. Next thing we want to ask, or next thing we want to know, is we know that these 2 waves combine, right? And then what happens afterwards? So does this red wave go back the other way, or does this red wave keep going, or do they just cancel out? So what happens is that the 2 waves, they sort of pass each other, and they just continue as they were. So if you remember that this red wave that was on the right hand side, and and this blue wave that was on the left hand side, they keep traveling and then just pass each other like nothing ever happened. In a perfect scenario, the amplitudes of this should remain the same. So if this had an amplitude of 3, this had an amplitude, we know that the red one had an amplitude of 5, the blue one had an amplitude of 3. Once they pass each other, the amplitudes should still remain. So this should have an amplitude of 5 and this should have an amplitude of 3. So essentially it's just the same wave that have passed one another. And putting it all together in an animation looks something like this. Yeah, so if this blue wave was instead going underneath, it was reflected in the x-axis. Oh, I can't see that. If this blue wave was going like this, it would be the same thing, but in the middle, the resultant wave is going to be smaller, and the waves will just continue as they were. So so if the wave on the right hand side keeps going to the left, you'll end up with something that looks like that. So the red wave that was on top remains on top. The blue wave that was on the bottom remains at the bottom. And so this brings us to this next thing about constructive interference. And put simply, constructive interference is just when you have two waves, they combine with one another, and the resultant wave is a lot bigger. So you can see that we have this wave. We'll just call this wave 1, and we'll call this wave 2. Let's draw this out. Yeah, so we have wave 1 and we have wave 2. And you can sort of imagine that as these two waves traveling on the same sort of string, or like the same, or maybe the same water, or the same slinky. And what happens is, because of the way the waves are, these two waves, you can see, it's like the exact same wave. And when they're traveling, the amplitude of these waves are, the amplitude of these waves are going to add, and you're going to end up with a wave that is about double the original size. And we call this constructive interference. The opposite of this is destructive interference. So what's happened in this scenario? We have, again, we have wave 1, we have wave 1, we have wave 2. And when you add these two waves together, so if they're traveling together, or if they're traveling towards each other, they're going to cancel out. And the reason they cancel out is, I'll just quickly show you. So if I just quickly sketch out the bottom graph and move this graph on top of the other wave. It's not a pretty illustration, but this is what you get. So what's happened? We just got this graph, this wave, and we moved it up. And then what this results in is a flat line. And the reason we get a flat line is because if you add the amplitudes of every single position, you're going to get 0. Right. So if you look at this point over here, so if we have this negative, we have this positive, they add up, and we have 0. So essentially, we have like +3 here, and we have -3 here. They add up to 0. The same thing for this position. It's not, again, I'm not an artist, but it's essentially the same thing. We have a negative number, we have a positive number, we add them two together, and we just get 0. And yeah, so this pattern will occur at every single point of the wave. And when you have something like this, where the two waves perfectly cancel out, we call this perfectly destructive. Oh yeah, and we call this destructive interference. So to make sure that you don't get confused between constructive interference and deconstructive interference, is that you can think of constructive interference. You think of constructive. Constructive means you're building something, you're making something bigger. So, so constructive, you're making something bigger. So therefore, constructive interference is when two waves combine to create a bigger wave. And if that's the case, deconstructive interference would be the opposite. So deconstructive meaning you're destroying something, and so in that case, you're destroying the wave, you're making it smaller. And yeah, so hopefully with that, you won't get confused between the two. Cool. So I want you to look at this image. So what's happening here? I'll just quickly describe what's happening. We have some waves. These are some water waves traveling through the water. And over here, we have some barrier. And what's happened is that the waves are going in this direction. The waves are going in this direction, and what happens is when it hits the barrier, these waves are spreading out. So you can see that this is the first wave, the second wave, and the third wave. They are spreading out in this sort of shape. And this sort of spreading out effect is what we call diffraction. So this wave is being diffracted and it's spreading out after it passes this gap. So this gap, is also called an aperture. If anyone's interested in photography, it's kind of the same idea. So the gap is basically how far apart is this, like this barrier. And depending on that and depending on the waves, that is going to impact diffraction. And diffraction, again, is just basically how much spreading do we have. Do we have? And it's the same sort of scenario here. So we have these waves. They've hit a barrier, and what's happened is that they've spread out, and it creates this sort of circular pattern. And yeah, you can see the same thing here. It's creating this sort of semicircle type of pattern. Yeah, one thing to keep in mind is this wave. So I can draw out this wave like this. So if that's a water wave, uh, these sort of like white parts, that is essentially our crest. Yeah, so crest being this part, so that's our crest, and this is our trough. So these parts where we have this sort of white parts, that is our crest. So that's our maximum amplitude. Our trough is our like these dark parts where the waves are like going down. And the same thing that's happening here. So these white parts, these are our crests. So these bright spots, maximum amplitude, that's our crests. These dark parts, that's our troughs because that's like the darkest part of like the lowest energy of the wave. And what you can see is that the wavelength, so we have this wavelength here. The wavelength is the same even after being diffracted. And the same thing here. So the wavelength, well, whatever this wavelength is, that wavelength gets continued after it's been diffracted. And so what we can do, we can combine all this information, and we get this sort of formula. Extent is this divided by, extent is this, wavelength divided by the width. The thing is, this is not really a formula. The thing is, because diffraction is not something you can measure. Like you can't say, oh, this is diffracting by 200 or this is diffracting by half. Diffraction is sort of like a qualitative thing. You can't really measure it. And that's why we have this sign, which is the proportional sign. So what this is saying that the extent of diffraction is proportional to the wavelength divided by the width. Wavelength is just the wavelength of the wave, and the width is the distance between the gaps. So if this is our setup, the width would be this distance, the distance between the two gaps. Cool. The next thing you have to keep in mind is this is a ratio. So the extent of diffraction is like proportional, or it's like the ratio of a wavelength divided by the width. So if you want to maximize diffraction, you want this value, or the extent of diffraction, to be close to 1. You want that to equal approximately 1. So when that happens, you get this. And when the wavelength and the width are of equal value, the ratio is going to equal 1. It's going to be close to 1. And when that happens, you're going to get maximum diffraction. Again, diffraction being how much does the wave spread out. And so when the ratio is near 1, the spreading outness of the wave is going to be maximum. If, however, the width is bigger than the wavelength, because the ratio is out of whack, it's not close to 1, the amount of diffraction you're going to get is going to be a lot lower. And the same thing will occur if the wavelength is much bigger than the width. Because the ratio is not close to 1, you're going to get less diffraction. So for example, let's just assume that the width is 1. Let's assume that the wavelength is 1.1. 1.1 divided by 1 will give us a value, will give us a value that's close to 1. And because it will give us a value close to 1, we're gonna see a lot of diffraction. But if the wavelength was really big, so let's say the wave was 200, this number is much bigger than 1. And because it's bigger than 1, we're not going to see much diffraction. Same thing will occur if we increase the size of the width. So if we make the width really big, let's say we make the width 1,000, we're not going to see much diffraction. And there's one thing I want you to keep in mind is diffraction can only occur on waves. So in other words, all waves can be diffracted. All waves can be diffracted, right? I want you to keep that in the back of your mind. So if you're making notes, yeah, just keep this in the back of your mind for a second, because it's going to be very important for the next topic, which is light.